we are going to start module 2 of chapter 5. In this module, we shall establish Hamilton's principle and will use it. So far, we have obtained Lagrange's equations of motion for constant motion of a dynamical system with the help of kinetic energy and virtual work principle. But in this module, we shall establish Hamilton's principle, which is basically an integral principle and very useful as it remains invariant under some specific choice of coordinates. Using differential principle, we shall establish Hamilton's principle here. In this module, we shall establish the Hamilton's principle from D'Alembert's principle. Lagrange's equation of motion will be deduced using Hamilton's principle. Also, Hamilton's equations of motion will be obtained using Hamilton's principle. Now, establishment of Hamilton's principle from D'Alembert's principle. Let us consider a holonomic conservative dynamical system. Let delta r vector denote the small virtual displacement of a typical particle having mass m of the system, whose position vector is r vector at any instant t. Then, from the generalized principle of D'Alembert's, we have among possible motions of the system, that motion is the actual motion which satisfies at every moment the equation summation over I mi ri vector double dot delta ri vector. Here mi ri vector double dot is nothing but the force vector, that is Fi vector. Therefore, we have summation over I mi ri vector double dot delta ri vector equal to summation over I Fi vector dot delta ri vector equal to delta W, as W is the work done by the forces capital Fi vector during the displacement dri vector. Since we have considered delta variation, so we obtain the delta W work, which is nothing but the virtual work done by the external forces capital Fi vector in virtual displacement delta ri vector. Now, ddt of summation over I mi ri vector dot delta ri vector minus summation over I mi ri vector dot ddt of delta ri vector equal to delta W, or ddt of summation mi ri vector dot delta ri vector minus summation mi ri vector dot delta dri vector dt equal to delta W. We have used the relation delta variation and ddt operation can be interchanged, or ddt of summation over I mi ri vector dot delta ri vector minus summation over I mi ri vector dot delta ri vector dot equal to delta W. Now, the kinetic energy of the system is capital T equal to half summation over I mi Ri vector dot square, since kinetic energy is half m v square. Therefore, delta T equal to summation over I mi Ri vector dot delta Ri vector dot. Here Ri vector dot is the velocity v. Substituting 5.3 in 5.2, we have ddt of summation over I mi Ri vector dot delta Ri vector minus delta T equal to delta W, or ddt of summation over I mi Ri vector dot delta Ri vector equal to delta capital T plus delta W, since delta W is equal to minus delta capital V, V being the potential field of the external forces capital F. So, we have ddt of summation over I mi Ri vector dot delta Ri vector equal to delta capital T minus delta capital V equal to delta capital T minus V equal to delta capital L, since the Lagrangian L is the difference between kinetic energy and potential energy in a holonomic dynamical system. We note that delta variation corresponds to a virtual displacement specified by the change delta r vector. Hence, delta variation is one in which time t does not change. We now consider the motion of a system in the time interval t0 and t1. Now, in the course of actual motion, a trajectory will be described in the configuration space. If we now allow the virtual change delta r vector at every instant of time, a neighboring trajectory will be described in the configuration space, and the changes in the Lagrangian capital L corresponding to the change in delta r vector is given by delta L equal to ddt of summation over I mi Ri vector dot delta Ri vector. Since the end configurations are prescribed, delta r vector at t0 equal to 0 and delta r vector at t1 equals to 0. If we integrate the equation 5.4 with respect to time t, then we get integration t0 to t1 delta L dt equal to integration t0 to t1 ddt of summation over I mi Ri vector dot delta Ri vector dt equal to summation over I mi Ri vector dot delta Ri vector considered at t0 and t1. Therefore, integration t0 to t1 delta L dt equal to 0, as delta Ri vector at t0 equal to 0 and delta Ri vector at t1 equal to 0. That is delta integration T0 to T1 L dt equal to 0, which proves that integration T0 to T1 L dt is stationary for actual path as compared to the neighboring paths between the same two configurations. Now, we shall deduce Lagrange's equations of motion using Hamilton's principle. So far, we have deduced Lagrange's equations of motion using differential principle. Here, we adopt another approach. By Hamilton's principle, we know that for prescribed n configurations at times T0 and T1, the integration T0 to T1 L dt is stationary for motion in actual path as compared to the motions in the neighboring paths between the same two configurations. That is delta integration over T0 to T1 L dt equal to 0. If we consider the delta variation under the integral sign, then we have integration T0 to T1 delta capital L dt equal to 0. Now, Lagrangian L is a function of generalized coordinate qk, generalized velocity qk dot and time t for k equal to 1, 2 up to n. Therefore, delta L equal to summation k 1 to n del L del qk delta qk plus del L del qk dot delta qk dot. By Hamilton's principle, we have integration T0 to T1 k equal to 1 to n del L del qk delta qk plus del L del qk dot delta qk dot dt equal to 0. Now, integration T0 to T1 del L del qk dot delta qk dot dt equal to integration T0 to T1 del L del qk dot delta dqk dt into dt equal to integration T0 to T1 del L del qk dot ddt of delta qk dt. We have used that delta and ddt operation are interchangeable. Integrating by parts, we have integration T0 to T1 del L del qk dot delta qk dot dt equal to del L del qk dot delta qk taken at the point T0 and T1 minus integration T0 to T1 ddt of del L del qk dot delta qk dt. On simplification, we get integration T0 to T1 del L del qk dot delta qk dot dt equal to minus integration T0 to T1 ddt of del L del qk dot delta qk dt. Since delta qk at T0 equal to 0 and delta qk at T1 equal to 0, substituting this in equation 5.7, we have integration T0 to T1 summation over k equal to 1 to n del L del Qk minus ddt of del L del Qk dot delta Qk dt equal to 0. For a dynamical system of n degrees of freedom, as delta Qk's are arbitrary and independent, so it follows that coefficients of each delta Qk must vanish separately. This gives del L del Qk minus ddt of del L del Qk dot equal to 0 for k equal to 1, 2 up to n, or ddt of del L del Qk dot minus del L del Qk equal to 0 for k equal to 1, 2 up to n. These are the Lagrange's equations of motion for a dynamical system of n degrees of freedom. In chapter 3, we have discussed detail about the Lagrangian mechanics and obtained Lagrange's equations of motion. Here we use the knowledge of energy, work and the virtual work principle. Using a differential principle like D'Alembert's principle, we deduce the Lagrange's equations of motion. But in this chapter, we have obtained Lagrange's equations of motion using a variational principle known as Hamilton's principle, which is nothing but an integral principle and valid for any type of coordinate system chosen. Now we shall deduce Hamilton's equations of motion using Hamilton's principle. By Hamilton's principle, we have for actual motion delta integration T0 to T1 L dt equal to 0 or integration T0 to T1 delta L dt equal to 0. We have considered the delta variation under the integral sign. Now Hamiltonian H is given by capital H equal to summation k equal to 1 to n pk qk dot minus L, or capital L equal to summation k equal to 1 to n pk qk dot minus capital H function of generalized coordinate qk, generalized momenta pk and time t. Therefore, if we consider the variation of the Lagrangian, then we have delta L equal to summation over k equal to 1 to n delta pk qk dot plus pk into delta qk dot minus delta H function of qk, pk and t. This can be written as delta L equal to summation k equal to 1 to n delta pk qk dot plus pk delta qk dot minus summation over k equal to 1 to n del H del qk delta qk minus summation k equal to 1 to n del H del pk delta pk. Substituting 5.11 in 5.10, we have integration T0 to T1 summation k equal to 1 to n delta pk qk dot plus pk delta qk dot minus summation k equal to 1 to n del H del qk delta qk minus summation k equal to 1 to n del h del pk delta pk dt equal to 0. Now, integration t0 to t1 pk delta qk dot dt equal to integration t0 to t1 pk delta dqk dt to dt. If we interchange ddt and delta, then we get integration t0 to t1 pk delta qk dot dt equal to integration t0 to t1 pk ddt of delta qk dt. Using integrating by parts, we get integration t0 to t1 pk delta qk dot dt equal to pk delta qk at t0 to t1 minus integration t0 to t1 ddt of pk into delta qk dt equal to minus integration t0 to t1 pk dot delta qk dt. Since the n configurations are prescribed at times t0 and t1, so delta qk at t0 equal to 0 and delta qk at t1 equal to 0. We have used these results. Substituting 5.13 in 5.12, we have integration t0 to t1 summation k equal to 1 to n delta pk qk dot minus pk dot delta qk minus summation over k equal to 1 to n del h del qk delta qk minus summation over k equal to 1 to n del h del pk delta pk dt equal to 0, or integration t0 to t1 summation k equal to 1 to n qk dot minus del h del pk delta pk minus summation k equal to 1 to n del h del qk plus pk dot delta qk dt equal to 0. Since in Hamiltonian mechanics the n generalized coordinates qk and the n generalized momenta pk have equal status, and since the result 5.14 holds for all arbitrary variations delta pk and delta qk, it follows that qk dot equal to del h del pk and pk dot equal to minus del h del qk for k equal to 1, 2 up to n. These are the Hamilton's equations of motion. In this module, we have discussed Hamilton's principle, which is a variational principle. Using this principle, Lagrange's equations of motion has been reduced. With the help of Hamilton's principle, Hamilton's equations of motion have been obtained.